Today we will discuss about a very interesting theorem from linear analysis. Uh, the theorem is let a function f close interval a comma b to r be continuous on close interval ab, and this function is differentiable on open interval ab, and given that if f dash x that equal to 0 for all x belongs to open ab, then the function is a constant function. This is a very well known theorem, and we use this theorem. But today we prove this theorem, and later that we will discuss a very interesting fact from this theorem. Let me prove this first. So uh, firstly, let 2 points from the domain. Let us take x1 comma x2 from the domain close interval ab. Okay, see, mind it that here we apply the LMVT theorem, that is Lagrange mean value theorem. So first we assume 2 point x1 comma x2 belongs to close interval ab, and a less or equal to x1 less than x2 less or equal to b. Why? Because these 2 points x1 and x2 belongs to close interval ab, so we assume that x1 is less than x2. Okay, now what is given that the function f is continuous on close interval ab. Since the function is continuous on close interval ab and differentiable on open interval ab, okay, then we can say that since this function is continuous on close interval ab and also differentiable on open interval ab, then this function is also continuous on close interval x1 comma x2. Why? Because these 2 points lie in this interval close interval a comma b, and given that the function f is continuous on entire the domain close interval ab, and x1 and x2 are 2 point in this domain a comma b. Since this function is continuous entire on the domain, then this function is also continuous on close interval x1 comma x2, and by similar logic this function is also differentiable on open interval x1 comma x2. So let me write this. Then the function f is continuous on close interval x1 comma x2, because x1 comma x2 is a point in this domain, and also differentiable on open x1 comma x2. Okay, now we ready to apply this theorem LMVT. Okay, now we apply LMVT theorem. So LMVT theorem says that there exists a point in open x1 comma x2. So by LMVT theorem, we can write, so what we can write? So by LMVT there exists a point, let C, that belongs to x1 comma x2. So I assume that we all know about LMVT theorem. So this is a very important theorem in differentiability. So what it says is said that there exists a point C that belongs to open x1 comma x2, such that f of x2 minus f of x1 divided by x2 minus x1, that equal to f dash c. Now see here, just a second. Okay, I use this. So here we assume that there exists a point C between open x1 comma x2. So now see the statement of this theorem. So what is given? Given that f dash x equal to 0 for all x belongs to open a comma b. For all x belongs to open a comma b. This is a very important keyword. So f dash x equal to 0 for all x belongs to a comma b. And see here, we take a point C belongs to x1 comma x2. We take a point C belongs to x1 comma x2. See here, a b, and we take from here x1 and x2. Okay, and by LMVT there exists C belongs to open x1 comma x2. That means C is here. C belongs to open x1 comma x2, and also C belongs to open a comma b. Okay, and given that f dash x equal to 0 for all x belongs to ab, then a particular point C in this interval open a comma b, then we can say that f dash c is also 0, because the word for all x belongs to open ab, f dash x equal to 0, and c also a point in between the interval open a comma b, then we can say that f dash c equal to 0. So right here f dash c equal to 0. So we get, what do we get? We get f of x2 minus f of x1, that equal to 0. So that imply f of x2 that equal to f of x1. See, since x1 and x2 be two arbitrary points in this domain closed interval a comma b, then we can say that f is a constant function. So let me write this. Since x1 comma x2 be two arbitrary points, on closed interval ab, therefore ab is a constant function. So this completes our proof. So now our proof is done, but now the fact is, let me explain. So see here, a function, let a function f closed interval ab to r. So this is the statement of this theorem. Now my question is that, is this result true if the domain is not an interval? So let me write my question. See here carefully that we take the domain is an interval closed interval ab, or you can take open interval ab, but instead of taking open interval ab, we should take closed interval ab, because the function has to be continuous on open closed interval ab. So my question is that, is this result true? Is this result true if we take the domain as an interval? This is my question. So we take here the domain is an interval. So if we take the domain is a set, or is this result is true if we take the domain is not an interval? Sorry, just a second. Is this result true if we take the domain? Sorry, just a second. That is my question. So let me define a function. So I define a function f from u to r. Okay, u to r. What is u? Here u is a set. Looks like u equal to open a comma 0 union with 0 comma 1. See, this is not an interval, this is a set. Open minus 1 comma 0 union with 0 comma 1. This is a set. So we take this set as domain of f and we define a function f from u to r, defined by how does this function define? Just a second. Defined by f of x that equal to minus 1 if x belongs to minus 1 comma 0 and 1 if x belongs to 1 comma 0. See here, we define a function u to r defined by f of x equal to minus 1 if x belongs to open minus 1 comma 0 and 1 if x belongs to 1 comma 0. We take the domain as a set. We take this domain as a set. The set is u equal to minus 1 0 union with open 0 comma 1. See here, the derivative of this function f dash x equal to 0, but is this function is constant function? Answer is no. See here, this function assume two value, minus 1 when x belongs to this interval and 1 when x belongs to this interval. So is this function is constant function? Answer is no. So we get a counter example. We get a counter example says that if the domain is not an interval, then the above result may not be true always. This is the counter example. This is a very interesting fact from this theorem. So